Type "how do I fix a car engine" into an old search box, and it hunts for those exact words. A perfect article titled "Automobile Motor Repair"? It never surfaces because it shares almost no words with your query, even though it is precisely what you wanted. That's the wall keyword search keeps slamming into. It matches letters, not meaning. But what if the machine could tell that engine and motor point at the very same thing? That's exactly what this method delivers, and it powers most modern semantic search. Let's dig in. At its core, the whole thing runs on one idea: turn text into vectors, then compare those vectors. Follow the pipeline one stage at a time. Start with your documents. A learned encoder reads each one and maps it to a dense embedding, a few hundred numbers that capture what the passage actually means. You compute these once for the whole collection and store them away, ready to be searched. When a question arrives, run it through the very same encoder. Now the query lives as a vector in the exact same space as your documents, so meanings that are alike sit physically close together, and unrelated ones sit far apart. Retrieval is then just geometry. Find the document vectors sitting closest to the query vector, measured by cosine similarity or distance. Closeness here means similar meaning, which is why a passage about automobile motor repair lands right beside a question about fixing a car engine. Hand back those nearest documents as the results. Notice what never happened. No exact word had to match. The system retrieved by meaning alone, which is exactly how it handles synonyms, paraphrases, and even different languages a literal keyword search would miss. So how is this actually different from classic search? Here's the contrast side by side. Keyword search needs the exact words to line up. It scans for documents containing your literal query terms, so if you and the author chose different words for the same concept, it finds nothing. Synonyms, paraphrases, and simple rewordings all slip straight through the cracks. This approach matches on meaning instead. Both the query and the documents become embeddings, and relevance is measured by how close their vectors are, so a passage can match even when it shares no words with the question at all. That directly solves the vocabulary mismatch problem. Strip it down, and 3 ideas define dense retrieval. It encodes both queries and documents into embeddings and matches them by similarity. A learned encoder, usually trained as a biencoder with contrastive learning, places related pairs near each other in vector space, so nearness reliably means relevance. It finds meaning even with no shared words. Because it compares concepts rather than characters, it gracefully handles synonyms, paraphrase, and cross-language search, which is exactly why it became the backbone of modern semantic search, and RAG can miss the exact term, so it pairs with sparse retrieval. A specific product code, a rare name, or an error string gets blurred into semantic space and slips past, and quality leans hard on the embedding model. That gap is precisely why hybrid search exists. Alright, let's lock in what matters. This method encodes queries and documents into dense embeddings and matches them by vector similarity, retrieving by meaning rather than words. Because it compares meaning, it retrieves relevant passages even when they share no keywords with the query, solving the vocabulary mismatch problem. Its blind spot is exact matches, product codes, rare names, error strings, which get blurred in semantic space and slip past. That weakness is why it teams up with sparse keyword retrieval in hybrid search. If encoding meaning into vectors clicks for you, there's a whole shelf of retrieval explainers waiting at standarity.com. Come find the nearest one.